Section 3.6, the chain rule. We've learned techniques for finding derivatives of polynomial functions, trig functions, sums, differences, products, quotients, and constant multiples of these functions. However, we still don't know how to find the derivative of a composition of functions. And that's what we're going to learn in this section. Let's start by looking at a simple composition of functions like h of x. H of x is made up of two smaller functions, like f of x is sine x. We're going to call this the outside function. And g of x equals x cubed. That's the inside function. If I were to do a composition of functions, like FOG, think back to your pre-calculus class. That's basically saying take the function g of x and stick it inside of the function f of x. And if g of x is x cubed, then that would look like plugging x cubed into f of x. And if f of x is sine x, that would look like we're plugging x cubed into sine x. So this is what we mean by a composition of functions. If we wanted to take the derivative of this function, we don't have any nice shortcut rules yet. We would have to start by using the limit definition of a derivative. Here I'm finding the derivative of h evaluated at a point A. And so we have the original function minus the function evaluated at A divided by x minus A, and we're allowing the limit where x approaches A. We're going to multiply and divide by x cubed minus a cubed. And we're allowed to do that because any number divided by itself is equal to 1, except for 0. So since that factor is equal to 1, we're essentially just multiplying the derivative of h by 1, which doesn't change the value of it. We can make some small changes applying limit laws and using the commutativity of multiplication. So I've basically just taken my denominators and had them swap places, and I've split my product to be two separate limits. Remember, there's the limit law that says the limit of a product is a product of the two limits. And we wanted to do that because doing so allows us to see that this second limit is following the format for the definition of a derivative. In fact, inside of that second limit, we can see the derivative of the function x cubed evaluated at A. And keep in mind that we've already designated the function x cubed to be called our inside function. So if we're taking the derivative of a composition of functions, we can now see that we're multiplying by the derivative of the inside function at x equals A. Now the only thing left for us to do is figure out what's going on in that other limit. Looking at that second limit, we can see a possibility for a substitution. I'm going to make the replacement where u represents x cubed. So anywhere we have x cubed in that limit, I'm going to replace that with the letter u. Making that substitution also has a consequence. X is approaching a in our original limit, and if x turns into a, then u would turn into a cubed. So we'll rewrite the limit, changing every x cubed to be now the letter u, and then allowing the limit notation to change from x approaching a to now u approaching a cubed. It wouldn't make any sense to leave the limit as x if we've taken all of the x's out of our limit function. Making these substitutions, we can now see that that limit follows the format for the derivative of the function sine u evaluated at u equals a cubed. So coming back to our derivative for h, we can now see that it's the product of the derivative of the outside function multiplied to the derivative of the inside function. We can continue with our derivative. We know the derivative of sine is cosine, so the derivative of sine u is cosine u, and then we need to evaluate that at u equals a cubed. That would look like cosine of a cubed. And then we also need to do the derivative of x cubed. That's going to look like 3x squared, and we're going to evaluate that at x equals a, so that would look like 3a squared. And finally, h prime would then look like the product cosine a cubed times 3a squared. What we just did was found that there's maybe a pattern happening here. For any composition of functions, we can take the derivative of the outside function with the inside still plugged in, and then the derivative of the inside function, and multiply those together to find the final derivative of the actual composition. In short, to apply the chain rule, what we're going to do is first identify the compositions. So find out what the outside function is, find out what the inside function is. Then we need to find the derivative of our outside function, and then plug in the inside function. That notation looks like this: f prime evaluated at g of x. Third step would be to find the derivative of the inside function, and then the fourth step is just to put it all together. This is from step 2, and this is from step 3. Let's give that a practice. H of x looks like a rational function, but it also looks like a composition of functions. The outside function looks like 1 over x squared. The inside function, the thing we plugged into f of x, looks like 3x squared plus 1. And if we wanted to test that we did that correctly, we could write our composition f of g of x, where we're taking f and plugging 3x squared plus 1 into it. And if f is 1 over x squared, then we would replace that x with 3x squared plus 1. So that would be our composition. So we have our outside function, we have our inside function. Our last example said to take the derivative of the outside function, so I'm going to call that f prime. That's going to look like the derivative of x to the negative 2 power. I'm rewriting that function using a negative exponent so that I can use my power rule. That derivative looks like negative 2x to the negative 3. But then as part of step 2, it says I need to evaluate that with the inside function plugged in. So if I take negative 2, well, I want to do one more step here, f prime with the inside function, 3x squared plus 1, plugged into it. And if f prime is negative 2x to the negative 3, then I'm just replacing x with the inside function. Step 3 then, so this was step 2. Step 3 says to find the derivative of the inside function. So that's g prime. So that's the derivative of 3x squared plus 1. That would be 6x. And then step 4, the final step, says to write the product of what you found from step 2 times what you found in step 3. So we're going to multiply this times this, and we're done. Now, when I say we're done, I mean we're done with the real calculus part of things. The last step would be to write this using some algebra manipulation to clean it up the best we can. So maybe we take our negative exponent and rewrite it using a positive exponent, and maybe we multiply the constants -2 and 6. So our final answer for the derivative of that composition of functions, h of x, looks like -12x divided by 3x squared plus 1 quantity cubed.